we move on from the great whack of deep impact to the lots of little whacks of the cometary particles hitting the Stardust spacecraft and the very careful catch performed by that spacecraft and then gentle descent into the Earth atmosphere. And to talk to us about this, we have Andrew Westphal from the University of California, Berkeley, who is an investigator on the mission and who is not only involved with the science, but also some of the extraction of these tiny particles from this amazing stuff you'll hear about called aerogel. He is also doing something truly amazing, which is slightly self-promoting because Planetary Society is involved with this, which is involving the public, as you will hear, in actual analysis of the data that has come back from the Stardust mission. So now I give to you Andrew Westphal.
Just a little over 3 months ago, the Stardust spacecraft brought back the first samples from the Kuiper Belt and from the local interstellar medium. Stardust is the result of a major effort by hundreds of people over many years, led by Don Brownlee at the University of Washington. The spacecraft was built by Lockheed Martin. The mission was run from JPL. I've listed some of the institutions now involved in the analysis of Stardust samples. This is only a partial list. There are actually 150 investigators worldwide, including Antarctica, who are looking at Stardust samples right now. And in addition, as I'll explain, we have 113,000 people who have signed up to participate in the search for interstellar dust in the Stardust collector. So this may be a world record scientific collaboration. So Stardust, just for a little perspective, is the first solid sample return mission since Apollo, and the first ever from beyond the moon. It's actually 2 missions in one. It's a mission to a comet. It's bringing back, it has brought back, the first samples from a primitive solar system body and a known body, a comet called Wild-2, a body which was formed at the extreme edge of the solar nebula early in the solar system's history. And it also is bringing back, and has brought back, the first samples of contemporary interstellar dust ever to be returned to Earth for study. So let me first talk about the comet. Don has actually given a great introduction to the reasons why comets are fascinating. And so I won't spend a lot of time on this, but let me just show a cartoon of the solar nebula as it appeared 4.6 billion years ago. The nebula consisted of, whoops, I'm going too fast here, consisted of a disk probably with bipolar jets coming from the center. The orbit of Jupiter is about here, and the orbit of the Earth, of course, is almost too small to see on this picture. The inner solar system was heated by the early sun, but the outer solar system, where the source, which is the source of the small short period comets, the Kuiper Belt, this is material which has been, we think, cold ever since the beginning of the solar system. It's been basically in deep freeze. And we have a unique opportunity to look at samples now from an object which came from that region and has only been in the inner solar system for the last 40 years or so. One of the first questions to ask about this when we get the material back from the comet is, have we seen this material before? Just a zeroth order question. And in fact, people have been collecting particles called interplanetary dust particles in the stratosphere for about the last 30 years. And a class of them called chondritic porous IDPs are loosely bound agglomerates of submicron rocks like this. And one of the questions was, is this coming from a comet? Many people thought so. We now think that the mystery is actually much deeper and that the material we're seeing from the comet does not look like this. So now we have 2 mysteries on our hands. Not only what is it that we're looking at in the comet, but where did this come from? And we also have the first sample from the local interstellar medium. It turns out that people have been studying interstellar dust in the laboratory for the last 20 years or so. But this dust is probably not typical of the dust that's in the interstellar medium. It's extracted typically from ancient meteorites. And these kinds of grains are present only at very, very vanishing levels, parts per million kinds of levels in ancient meteorites, and can be isolated from meteorites only with quite harsh chemical separation techniques. So as somebody in the field said, it's a little bit like burning down the haystack to find the needle. This is a typical silicon carbide grain. It's found in interstellar, in ancient meteorites. It's interstellar, and the only way we know that it's actually interstellar is because it has very bizarre isotopic ratios. One other thing that we want to look for in the sample of material from real interstellar dust, a much more unbiased sample, are certain enigmatic particles called GEMS. It's an acronym. It means glass embedded with metals and sulfides. These are really weird objects which no one understands, which have been found in interplanetary dust. We want to see if they're present in the interstellar medium. And this is a subject that's of particular interest to our group at Berkeley. Let me talk a little bit about the mission. This is really fun. So Stardust is a discovery mission. It's in the Discovery line of spacecraft. The Discovery spacecraft are planetary science missions which are inexpensive but can provide very high value for the dollar, science value. In fact, the cost of Stardust was about the same as over its 10-year mission as that of a highly paid baseball player. So that puts it in some perspective. Okay. And the Stardust spacecraft had a collector on it made of aerogel. I'll talk about that in a minute. It was actually a two-sided spacecraft corresponding to the two missions in one that I talked about. The back side collected interstellar dust. The front side, which you can't see here, collected cometary dust. I really encourage you to look at the launch video that was taken when it launched in February of 1999. A rocket from a camera that was mounted on the side of the launch vehicle. It's great. You can almost see the blades of grass around the launch site, and you see it all the way up into interplanetary space. It's great. So I highly recommend going to the JPL Stardust website to look at that. So this was 7 years ago. And in that time, it had quite an adventure, series of adventures. It actually collected interstellar dust during two periods, during the cruise phase before the encounter with the comet. And it collected interstellar dust at times in which the spacecraft was moving with the stream of interstellar dust, which is continuously streaming into the solar system. So about 150 days of collection time for interstellar dust on the backside of this aerogel collector. It had an Earth flyby to get it into the right orbit to be able to encounter the comet, and it also had a serendipitous encounter with an asteroid called Anne Frank. But the real fireworks were in January 2004 when Stardust flew through the coma of VIL 2 with a relative encounter speed of 6.1 kilometers a second. Now that sounds fast, but it is actually incredibly slow on the scale of these things. And it enabled us to capture dust because it was such a slow velocity, we could capture dust, in many cases, practically intact. And in January of this year, Stardust came back. It returned in a fireball over Northern California and Nevada, and landed in the Dugway Proving Grounds in Utah. And I was very, very privileged to actually see it. Very lucky because it was a cloudy day in Nevada, and in fact there were blizzards, and we drove through a blizzard about 15 minutes before we saw this thing actually come in. I had my kids, who were only 5 and 8, in sleeping bags on the hood of my car at 2 o'clock in the morning in the cold desert. They'll never forget it. It was amazing. Okay, and this is the capsule as it was found. Oops, one of them too fast. As it was found in the mud, on the mud flat at Dugway Proving Grounds. And so this was a great day for extraterrestrial materials research. And here's the tray now in the clean room in Houston at the Johnson Space Center, being peered at by fascinated scientists and incredibly excited scientists, I have to say. Absolutely unforgettable experience. Now let me talk a little bit about the collector, because the collector is very unusual and presents a lot of interesting challenges. The collector is a weird material called aerogel. It's a silicate nanofoam. It's got the same chemical composition about as glass. It's a silicate material, but it's only about 10 times as dense as air. And I can tell you, having worked with it for many years, it is weird. It has very bizarre mechanical properties, but one of them that's really wonderful is that it can capture particles going at many kilometers a second practically intact in many cases. Not always, but certainly better than anything else. One of the big surprises when we got this back was to see these big, I keep pressing the wrong button here, these big impacts right here that are almost a centimeter across. These are huge. We weren't expecting to see anything like this. These, in fact, present their own technical challenges, but it's wonderful to have so much material to work with. From the side, here's one of these tiles of aerogel having been pulled out of the tray. You can see now the track of a cometary particle. And just as we thought would happen, this material broke up in the process of being captured because we expected it to be fairly friable, fragile material. And in fact, that is what happened. We have lots and lots of little particles all around this track, and then down here, a very large mineral grain, which goes deeper into the aerogel. Now, the big problem is, or challenge, how do you get this stuff out? You can't just use a razor blade, which is what you might think. You'll just make a mess. So it turns out that we've developed new technologies, actually, for extracting these particles. And that's actually been mainly our role up at UC Berkeley. And we've borrowed tools from microbiology labs. We use robotically controlled glass microneedles to extract particles by machining the aerogel on a tiny, tiny scale. And this is a process that takes hours and hours, but it's all robotically driven. So we can just set it up at the end of the day, let it run overnight, and in the morning it's done, which is great. And here is something we call a keystone. It's a little wedge-shaped piece of aerogel which contains the track of a cometary particle with the cometary particles strewn all along it, mounted on the end of a little micro-machined fixture, silicon fixture. This is actually coming out of a Stardust tile. And there is a cometary particle here on Earth, brought back from a comet by the Stardust spacecraft. And just as we expected, you can see these particles have broken up. We have a little spray of particles all along this track. And here's the fixture for holding it. This piece of aerogel is so light that you have to have some way to hold it. If you don't, it'll just, by looking at it, it'll just float away. You'll lose it completely. So this has been a huge amount of fun, just learning how to handle this stuff. We've also developed some special tools in collaboration with people up at Berkeley who specialize in micro machines. This is a micro machine tweezer that can handle micron-sized particles. And now we're only 3 months, a little more than 3 months since recovery, and I can't actually tell you most of what we found. We found a lot of fascinating things, but we have an embargo on information until we actually have it published. But I can tell you some things, and in fact, I can tell you one of the most important things that we found. So, but let me give you some examples of some of the first things we looked at. So here's a cometary particle extracted in one of these keystones right here, and then the particle at the end of this track was pulled out on Valentine's Day by Keiko Nakamura at JSC, and it's kind of amazing. I think Stardust gave us a Valentine's Day present. Here is a 2-micron grain of olivine. Olivine is a silicate mineral, and you can see in this picture a rim of molten and compressed aerogel in which this stuff was captured. This is actually a view in a transmission electron microscope, which can allow you to really see these minerals up close and in detail. But this next picture makes the entire mission, all by itself. Even if we find out nothing else about this material, this is actually stunning. Let me explain why. The materials we're seeing here are anorthite, diopside, spinel, and some bizarre, very bizarre minerals of vanadium titanium nitride, which is called osbornite. These are all very high temperature minerals that had to have been formed in an extremely hot environment. And so the real puzzle is, what in the world are these hot minerals doing out at the edge of the solar system in the coldest part of the solar nebula? No idea, frankly. Well, that's not quite true. Of course, once you have an observation, people step up to the plate and come up with ideas. So there are ideas, but we have no idea which ones are right, if any of them. And it may take quite some time to sort this out. It's possible that there is material that was transported from the inner solar system to the outer solar system early in the solar system's history. It's possible that these things actually got heated out there by some mechanism that we don't understand. It's even possible that some of this stuff came from other stars. We just don't know yet, and a lot of these mysteries will be solved when we look at the minor element and isotopic compositions of these grains. So stay tuned. Okay, I want to put in a plug now for the general approach that this mission took, which is to bring back samples. It's a sample return mission. This is stolen from Don Brownlee, but I just love this slide. So the inset is a painting of a comet that was observed over Paris in the 1850s. And the size scale is rather large. And it's overlaid on our current view of a comet in a transmission electron microscope. And you're actually seeing the material, the mineral in the comet at the atomic scale. So by bringing back a sample of a comet, being able to study it here in the laboratory, or in many laboratories all over the world, we've improved our resolution by about 20 orders of magnitude in our ability to measure and understand comets. So, but let me be a little bit more specific. The advantages of bringing back a sample. You can use instruments that could never be flown in space. A good example of this is the Advanced Photon Source, which is a synchrotron at Argonne National Lab near Chicago. It's the size of a shopping mall. You'd never be able to fly that in space. Well, maybe I shouldn't say never, but not anytime soon, that's for sure. You can take advantage of advances in analytical capabilities. There are several instruments that are now being used on Stardust samples. The NanoSIMS instrument, for example, which does isotopic mapping, which weren't even built when the Stardust mission was launched. This is in contrast to missions in which you have to fly an instrument and you have to lock in the design of the instrument well before the launch, so it's guaranteed to be obsolete by the time it launches, let alone by the time it actually makes the measurements. You can study these samples for decades and take advantage of the new kinds of instruments that will be available 50 years from now. And another way I think to look at this is that this is really human exploration. Rather than humans going after the comet, which is very expensive, you can actually bring the comet back to the humans. And it's a lot more, it's a lot less expensive and considerably safer. Okay, now let me talk about the second mission of Stardust, which is to find interstellar dust. So before we can even analyze the interstellar dust that we have in the collector, we have a challenge ahead of us, which is to find these dust grains. Let me talk about that in a minute, but first, let me tell you about the people participating in this part of the project. This is really led by UC Berkeley, it's funded by NASA. We have collaborators at NASA Johnson, at JSC, and we're partnering with the Planetary Society and the University of Washington and the University of Heidelberg. So our challenge is, how do we find roughly 50 to 100 submicron grains in about a square meter of aerogel? This is a huge challenge because we have to find these things, we have to search for them with high power microscopes. And the problem is that we'd have to search, if we were doing it by hand, we'd be searching for years and years and years. And we might even miss a lot of them because it would be so boring to have just a few people doing this and finding mostly blank fields of view that we'd probably never finish. So what we're doing is we're collecting digital images of the collector at very high magnification. Now, when we started this project, we assumed that we would use some sort of computer to recognize the tracks in the aerogel. And so we thought a lot about this problem, and talked to some experts at Berkeley, including one of the world's experts named Jitendra Malla. They can do amazing things with automated recognition algorithms, picking out letters in distorted images and all kinds of amazing things. One of my favorites is this, the automated detection of human nudes. This has a practical application in internet pornography filters. If you can build something into your browser that will keep pornographic images out, you can let your kids, use the internet more easily. But this image actually is from an academic paper. Shows these are images which the algorithm that they developed for automatically detecting human nudes incorrectly flagged as being pornographic. And I'll leave it up to your imagination as to why. But our conclusion really was that at least we don't know how to write an algorithm. It may be possible, but we don't know how to write an algorithm to find these tracks. And we have to search over 1 million fields of view to be able to find them. So talking to our friends down the hall at the Space Sciences Lab who started the SETI at Home project, we thought that it might be possible to enlist the help of volunteers. So we've developed a web-based virtual microscope that works just like a real microscope. It uses, of course, images collected from this automated digital microscope that is right now scanning the interstellar collector at Johnson Space Center in Houston. The virtual microscope works by just simply moving a mouse up and down a slider bar, and this will focus the image up and down, just as if you were sitting in a real microscope and focusing up and down by hand. So it's written in JavaScript and HTML, so you don't have to download anything. You just can use it straight away, right in your browser. And we've just finished, in fact, a load test with members of the Planetary Society, which worked great. And it's worked great in two senses. One is that it worked great, and the other is that they've given us a lot of good feedback as to how to improve it. So it's going to be even better. And so this is the basis of Stardust at Home, and you can go to our website at stardustathome.ssl.berkeley.edu and pre-register, and we think in just a few weeks, 2 or 3 weeks, we're going to be launching this with real data to search for interstellar dust. And I should just say we had an accidental test of this early on, which is kind of fun. So a colleague of ours leaked, and we're glad they did, although at first we were a little frustrated, but they leaked the address of the development version of our microscope to a teenage chat room. And we suddenly noticed all this traffic, and we didn't understand what was happening. And, hey, are you using it? Are you using it? No, nobody's using it. We're getting all this activity. So one of us actually joined the chat room just to see what they were all saying. And they were all saying, hey, this is just really fun. Let's do some more. And, but it also had a side benefit. It allowed us to see how well they were doing. It turns out we had calibrated images we already knew about that had tracks in them and didn't have tracks in them. And so we could actually see how well they did. And it turned out they were amazingly good at it. They were 95% efficient in finding tracks. So this was real encouragement that that this would work. So by now, more than 113,000 people have pre-registered. And please join. Thank you.
Thank you. We are running late, no fault to Andrew or Don. Why don't we take one question and then unfortunately we'll have to move on.
Something I have seen discussed nowhere in mission literature. While the collectors were being exposed to collect the interstellar dust, it was also being exposed to the background interplanetary dust. What was the expected impact flux in the front and rear panels of oblique impacts, since the dust would come in at random angles?
That's an excellent question. One of the great advantages of using aerogel is that you have trajectory information. So you can see where the particles are coming from. And that enables us to measure the interplanetary dust flux on both sides. And actually, we're really quite surprised. I think I can say this. We haven't found any interplanetary dust particles yet on the cometary side, which is actually, we're not sure whether that's surprising yet or not. But anyway, There doesn't seem to be any contamination at all so far from interplanetary dust. We're only looking at comet dust. Thank you, Andrew.
Thank you, and thanks, Andrew, for not only doing science, but getting the public involved with it through this very creative Stardust at Home activity. Also, by the way, Andrew gave us some of, when he was out there in the desert with his kids on the hood of his car, he gave us some of the best live radio I think we've ever gotten in our weekly planetary radio show. So if you want to hear Andrew get really excited, go to planetary.org/radio and go to the archives and check that out.